Hello everyone. Thanks for joining today's webinar. Uh, let's wait for a couple of minutes. People are still joining. I see the numbers increasing. So let's give some time. So meanwhile, can someone confirm if I'm audible and you are able to view the screen? I've shared my screen. That will be helpful. Uh, Benjamin, you can type it in the chat window if it is possible. Like, you should be able to uh, type in the chat window to confirm. I see your hands raised. Looks and sounds great. Thanks for confirmation. Thanks. Okay, just give a couple of minutes and then we'll start. Okay, let's get started. So a formal welcome, warm welcome everyone. Thanks. Good evening, good afternoon, good morning. Everyone who has joined this webinar on performance optimization of butterfly valve with autonomous valve CFD. So this is our topic today. So let's jump into the webinar now. Okay, so first I'll introduce myself. Uh, myself, Praveen Kumar. I'm the product marketing manager at Simulation Hub. So I'm basically a mechanical engineer with a PG diploma in CFD. So I have around 15 plus years of experience, working experience in CFD projects across various domains, including valves, HVAC, aerospace, a wide range of domains I've worked on. And then moved into product management after completing a certification course in from IIM Indore, and then now in the marketing field of it. So yeah. So we are into developing cutting-edge CFD technologies for valve industries, specifically in today's context. So this is the agenda of the webinar, today's webinar. Like we'll see what is butterfly valve and what are the flow performance data. CV and CDT will cover those and the methods to determine the flow coefficients. Like what are the different methods and what are the pros and cons of different methods. And then slowly we'll introduce the autonomous valve CFD platform and app working demo or demonstration. And we'll have a case study where we'll take a real life case study where our customers have applied, used autonomous valve CFD to optimize the butterfly valve design. And then we'll end with the Q&A session. So in between, if you have any questions, you can post them in the chat window or the questions, options. So we'll address those questions together towards the end of the session. So what is butterfly valve? It is a rotary type of valve, which has a butterfly shape disc that opens and closes to allow the flow medium through pass through and in order to regulate or isolate the flow. So what are its advantages? It's very simple in construction. You can see the parts are simple: the disc and the shaft, and the valve body, and the lining things. And it is actuated by manual or the electrical or hydraulic. So this is there. And then the dimensions and it occupies less space while installation. So and also it comes with like it's very cost effective, less material and weighing less, and it provides tight sealing. And due to its quarter turn operation from fully closed to fully open, it's very rapid opening and closing cycles it provides. So these are the advantages of butterfly valve, and the applications are very versatile across different industrial areas. You can see here. And then talking about types of butterfly valves, you can categorize them according to based on the valve body type, wafer lug, and everything, and actuation type, everything. But in today's context, the design, speaking about the design, it can be majorly categorized into three types. One is the depending on the offset. Okay, so zero offset or centered butterfly valve, or double offset, double eccentric, and triple offset or triple eccentric. So the eccentricity, what we are talking about, or the offset we are talking about, what we are talking about is, you can see clearly. So between the disc and the shaft, the rotating axis, and then from the center of the disc, there is another offset. And same thing for triple offset, you'll have a additional offset. You can see in the double offset, you can see both the ends are the cone. If you draw a cone, it intersects at the center. It's very symmetric of the third offset. Whereas for triple offset, if you draw the cone, the top portion or towards the pointer, you can see the flat line and there is an angled. So the cone is also offset. There is a third offset. So the applications are different for each. So for metal to metal contact, high performance and more like less leakage. So depending on that requirement, the different types are chosen. So now that we have set some, foundations for butterfly valves, just to keep everyone, I understand, people attending the webinar coming from the valve background. So you guys know better in terms of the, valve application and things. So we talk about CFD. So I'll quickly move on to that. So I just wanted to cover, there might be some people who are catching up, like you have fresh. So I just want to touch base on. So the next thing is, before we go into the jump into the core topic, I came across a article or a case study from IMI. So which, I thought I would be sharing. It will be helpful if I share this. It's a food for thought kind of thing. So this is a case where there is a major offshore oil and gas facility where they faced problems. They were experiencing problems in the second stage water transfer pumps. So upon inspection, the valve was it was frequently failing, and after inspection, they come to know the valve which was already installed, a third part, like some other manufacturer existing valve, was designed to handle a maximum flow rate of 257 meter cube per hour, and the actual requirement for the state, pumping the uh, transfer water, that is 310 meter cube per hour. So that is has been putting strain on this whole system. That started affecting the all the complete systems connected to them. So an undersized valve. So this is the typical case of undersized valve. So it experience high pressure drop across the valve to maintain flow and everything. So it is risking the damage to upstream pumps or other equipment. So an undersized control valve generally, it cannot deliver and puts a lot of strain. So we are talking about sizing, right? So what defines the numbers? right? What defines the numbers? What defines the numbers is like that is the flow capacity. So let's see officially what is the we have two flow performance data, I would say. So the first one is very critical, the valve flow coefficient CV. So this, like you might have seen, this is the table, data table, like CV table you have to produce across all your valve sizes and for the complete opening. So this is just a sample typical CV table or CV curve, I would say. So flow coefficient CV, that is nothing but the volume of water that will flow through the valve uh, across when the pressure drop is like 1 psi across the valve. So 1 psi is the like per unit pressure drop. That's what I would say. It's not exactly 1 psi. So the definition, what it means is across the unit pressure drop. Per unit pressure drop, what is your flow capacity? Okay, that's what it means. So this is the formula to calculate. SG indicates the specific gravity of the fluid. So water is usually used, and water at temperature at 60 Fahrenheit is used. And then if you want to calculate the flow capacity, if you're using a different temperature water, or if you want to calculate the flow capacity for a different medium, then you use this SG, modify this, and then you can calculate the flow rate or flow capacity. So it is calculated for every angle of opening from fully closed to fully open. Okay, the complete CV curve looks like this for one valve size. Okay, so this table I was showing for each and every valve size, you'll have this complete, individual curve. So similarly, the next one is hydrodynamic torque coefficient. So hydrodynamic torque is nothing but the turning moment due to the difference in fluid forces across the on the rotating body. So when the flow happens, there is a due to the difference in flow velocity around the leading edge and the trailing edge, there is a difference in pressure forces on the both sides of the rotating body, and that causes a closing torque. So that helps in actuator sizing and selection. So we saw uh, a case of undersized valve. So this is the flow rate related, falling short of the required flow capacity that corresponds to CV. So that will help you to rightly size the valve. And the second one, the hydrodynamic torque, or CDT, the coefficient part. So that will help you to size the actuator required to operate the valve, right? So in that selection. So here we are introducing the coefficient of dynamic torque, hydrodynamic torque. So that is a non-dimensional number. CV has some units, right? Like CV has GPM per PSI. That unit is there, but this one, CDT, is a non-dimensional representation of the dynamic torque. So how it is calculated? So if you know the dynamic torque and you know the pressure drop across the valve for the valve size, then this is the valve diameter. So you get the CDT. Again, CDT is calculated throughout the valve range, operating range, and you can see a typical CDT curve of a. This is for a zero offset or centered butterfly valve. Okay. So the offset valves will have a different pattern of CV. It will have a torque reversal and things. So we'll see those in later slides. So now we know CV and CDT, how CV and CDT are, evaluated or calculated using the flow loop test. Okay, so that is the first thing. So what is flow loop test? It is nothing but the tests conducted in the flow labs based on the according to the standards. Methodology is defined in these standards. For example, ANSI ISA 75.02.01 standard, and these are conducted in certified laboratories like UWRL, Utah Water Research Laboratory, and FCRI in India. So there are many such labs, and the CV and first I'm talking about CV. So it has this is the complete line diagram which shows what is the setup to measure the flow capacity and torque. So it needs this is the VAR test specimen. installed, and the pressure tappings are installed upstream and downstream. Upstream, you have to install a 2D diameter and then 6 times the diameter of the test specimen, the valve we are testing. So 6 times on the downstream side. So yeah, and talking about CDT, what they do is the test setup remains same, the 2D, 6D, and all those things remain same. And additionally, there are few like formulas and things given in the AWWA M49 standard. So where you install the strain gauges on the valve shaft, and then that will provide you the torque, opening torque and closing torque. You do from open to close and close to open, and then you calculate the dynamic torque, and you get the CDT by using this formula. Okay? So again, the pressure tappings and the other flow setup remains same. It is same as that of the CV, the previous thing. So typically, it is the readings are taken in three different flow rates to make sure there are the measurement is not made in a cavitating zone or region. So we should not be in the laminar as well, and we should not be in the cavitating zone as well. It should be in the turbulent non-cavitating zone. So there are guidelines given in this what Reynolds number should be achieved, and all those things are there in the standards. So now we have seen the methodology to calculate CV and CDT. So let's say what happens in a new product development. Okay. So what happens is, let's say you have a new requirement, design requirement from end client, and the target, there is a target CV. So this is the CV that needs to be achieved or something. So it's a new design, let's say. Okay. So the design engineer designs the valve, and then it is the prototype is manufactured and then transported to a flow loop test facility, which is most probably remotely located, and then the flow loop test facility conducts the test and provide you with the flow performance report. So it has the CV and CDT table and everything. Okay. So what happens is it typically takes results takes weeks of time. I'm talking only about the testing time. If I include the transportation and the manufacturing, so it goes in queue, right? So the flow loop test facilities are limited in number. They have a lot of orders. So your valve test goes in queue, and that's how it is. And what you get out of it is the report which has the CV and CDT value. And let's say if your CV value doesn't match your expected or target CV, so you will not get any clue what went wrong with your baseline design. Of course, the flow loop test facility report provides you the current baseline designs uh, capacity, flow capacity, but what went wrong? So that insight is not possible. So what are the challenges in flow loop test? So it provides you with the limited flow insight. So whether the CV is dropped because of where the flow separation regions are, where I need to work on. So that flow insights is missing. So what is happening inside? It's missing. So it will give you 2D and 6D pressure drop, and then the CV. That's it, right? So that is one challenge, limitation. And then the any design changes will cost you, like it will be of like cost and time will be more. So you have to go through this loop again, the design changes, and manufacture the prototype again, run it back to the facility and run the test again. So this is consuming more cost and time involved in any design changes. And of course, resource limitations when it comes to large diameter valves. So we'll see one real life case study, and towards the end of this webinar. It's from one of our customers, so it's very interesting case study. So there, large size valves, particularly the flow loop test facilities, also have some limitations in running tests for such large diameter valves. So imagine the amount of volume of water required, and it should be recirculated, pumping power required. So it's a huge task. as the diameter increases, the testing cost also increases, and the time, everything increases. Yeah. So here is a what is the alternate methods for flow loop test then, right? It takes more time and cost for design iterations. So of course the accuracy is the closest, right, to the real thing. So that is the real ground truth. So close to the ground truth, I would say. Time and cost, and so it's more. On the other hand, the alternate methods include analytical and numerical method, CFD. Of course, the analytical method has gives you less accurate, but it gives at a very quick, and the cost involved is also less, but the accuracy is compromised. So what happens with the numerical method? Yes, it is considerably less time and cost than the flow loop test. If you consider the design iteration part and things, accuracy is much, much, much better than any other methods, and it is closer to the flow loop test when done right. So when I say when done right, that's where the skill part comes. So you need expertise and experience dealing with CFD simulations to get a meaningful and accurate results out of CFD. So what are the challenges in analytical method? So less uh, it has the there are few things which are missing, you know. So it doesn't account for all the local flow separation, swirls, and all the local geometrical variations. It's a generic thing, right? So there are some empirical adjustments you need to do, and you'll not be very sure about this. So these are the challenges of analytical methods, and now we are moving to the CFD part. So what is CFD? CFD or numerical method is like computational fluid dynamics. It stands for computational fluid dynamics, CFD. So that is it's a science of predicting the fluid flow and heat transfer, mass transfer phenomena by solving the governing equations in a mathematical equations in a numerical form. Okay? So in a discretized form, I would say. So in order to do that, we need to discretize the fluid domain into um, shapes, cube shapes, or some defined shapes called cells or mesh, right? So this is where mesh comes into picture. So this is nothing but a system of algebraic equation. You can see the Navier-Stokes equation, which is the governing equation in this case. So that is solved numerically on a computer. In order to do that, we discretize this equation as well as the governing, sorry, the fluid flow. Okay. So that then these equations are solved at each node or cell of your mesh. Okay. So what is the process looks like? We can categorize the CFD process into three major steps. One phase is pre-processing and solving and post-processing. This is the process actually solving and pre and post. So you're preparing your geometry or CAD model. So it starts with the CAD model itself. That is the bare minimum input you can it's required. Then you convert that into discretized form, which is mesh. And then you define the boundary conditions, so and then you give it to the solve actually. Here, this is the major computationally costing time-taking part, and then you visualize the results. So this is the very insightful visualizations you get visualizing the post-processing part. So you have different tools to understand how your flow behaves inside. So what happens is this is the benefit of CFD. So flow insights from virtual in like flow loop testing or CFD. So the pressure values at any location, not just at the 2D and 6D, and flow separation, location of lowest pressure. So everything is available. So you can use the post-processing tools to get those insights. So in a conventional CFD approach, what happens is you start with the CAD model, you extract the fluid volume and generate mesh in the fluid volume and define the boundary conditions and select the appropriate turbulence model and numerical schemes, you know, in order to get the meaningful, accurate results. So the computation part, you need a HPC setup in-house to run this simulation, like run the CFD simulation. It takes hours of time, and then finally you get the results, and you need to use these reports, do some post processing, and then get the curves, do the calculation, get the curves, and then create the report, right? So this is the conventional approach. What are the drawbacks? So the CFD knowledge or expertise is required. So that is the very first challenge you will face as a valve designer, I would say, valve designing community. So, and also it requires high power computing machines in-house. And addition to that, the software, whatever you're using, that has its own added cost and annual maintenance fees and upgrading the installation. So all those parts comes into picture. So in order to address these challenges, we at Simulation Hub, we developed platform where where multiple applications are developed, so which are cloud based. The simulation should be on cloud based. It's a upfront CFD simulation, and it is tailor made for designers, not the special analyst. So that is the vision, and to democratize this technology and take this technology to the hands of every designer. Okay. So it is powered by Autodesk platform, AWS for cloud simulation, and OpenFOAM is the CFD solver which we use in the backend. And we are bringing more and more solvers as an alternate option also to have better to have more capabilities and things. So in today's context, like we are talking about one such app from simulation of platform, which is Autonomous Valve CFD. So we refer to this as a virtual flow loop test because it mimics the actual flow loop test, and to provide you the CV, CVT, or incipient cavitation index and such things. So we it follows the standards or the guidelines from these standards like what is done in the actual flow loop test. Okay. So what happens? How it works? So the inputs required are simple. So you start with the CAD model, okay, and you specify what is the flow direction and what opening conditions you want the simulation to be performed. That's it. No other additional, very CFD specific inputs are not required. The app handles it in an autonomous way. So we'll see how it works. And then it provides you with a set of post-processing tools with which you can obtain velocity contours, surface pressure, flow lines. So all the typical outputs of a CFD simulation. So and also you get the performance data. So these are qualitative results we call, and then this is quantitative data. So CV, CVT, head loss coefficient, cavitation index, all those curves and tables are available, and then you put it in a. So the report is automatically generated, and you can download it in a PDF format with your branding added and everything. So your organization branding added. So it is ready to submit to your end client. So that's the idea, and it supports all type of valves in ball valves and butterfly valves, all different types of ball valves and butterfly valves, globe valves, so all categories. And in today's topics, like it covers all the types of butterfly valve. And what you need is a web browser. It's a cloud application and it's a web application, so you don't need any installation. You need a browser. Go visit the website, login, and you end up in the dashboard, and you start simulation. So you need an internet connection, and it works on your laptops and machines, desktop machines as well. So the workflow is very simple. As I said, you need to upload your CAD model, you specify the flow direction and solve it on cloud and view the results on browser. So let's look at a demo of the app. Okay, let me, yeah. So as I said, this is a web application. So this is on your browser. So you have logged in to your account, logged into your account, and here this is the dashboard where you have all your old projects, and then you can create a new one. So you specify the description about the project and everything for your reference. And here you're uploading your CAD model. So So we support IPT, part models, STAPE, IGS, and SolidWorks. So all sort of things are supported. So then once it is uploaded, then you can visualize the CAD model on your browser. So this is the Autodesk platform services that we are using. So you can view your CAD model, view the cut section, measure things. So all those things can be possible. So you can see the tools here. Okay, and then you specify some valve details, whether it is a control valve or isolation valve. So it's a rotary valve. Right now, what we have is a rotary valve, butterfly valve, triple offset, I guess. Yes, and around 400 diameter. The pressure class and pipe schedule. So all those details, pipe roughness, valve roughness, you can specify. Then moving on to the next step, which is moving parts selection. So here you're selecting, in this case, the moving parts are the disc and the shaft. So that's it. So you specify this and you specify the axis of rotation. So around which the stem shaft, basically around which the valve rotates. And you specify the opening conditions, so starting to end position and number of like frequencies or steps in between the minimum and maximum. So you can see the percentages and you can have a preview. So if it is in the reverse direction, you can reverse the rotation direction also. So the next step is defining the valve connection. You're selecting the inlet and outlet pipes. Okay, that's it. So you have reached the simulation or solve stage. So this is the minimal like the inputs required to start your simulation. So at this stage, you submit your simulation, and the simulation runs on all the simulations, for all the openings, runs on the cloud. So you can see the fluid volume has started. So once that is done, then the mesh happens, and then the solve happens. So once during this time, you can even log out and go because the simulations are running on the cloud. So once you get a notification, that email notification from the app that the simulations are completed, you can come log in back and then continue from where you left. So yeah, so it provides the quantitative data, uh, and then the curves and other tools, right? You can see the detailed values. You can export it in CSV format and things. So, and then the flow line animation. So these are 3D visualizations. So you can animate it and get the insights. So where there are swirls and flow recirculation happening. So another tool which is contour plots. So section wise you can visualize where there are flow circulation or where the velocity is high, velocity is low. You can see, for example, the blue region, after the downstream of the shaft or near this disc. So that indicates there is a low pressure or like the pressure drop is happening. So sorry, that's not low pressure, that is low like velocity. So that's where the pressure is, the energy is getting consumed. So recirculation thing happens. Okay. So moving next, there are some more tools. Here you can visualize the pressure contours as well, and then surface pressure. And this is the report you get out of the app, auto-generated report. So it has all the details, all the simulation setup, what flow conditions were used, and what flow mediums are used, what formulas are used to calculate. Yeah, so that's it. So it's pretty simple. It looks simple, right? But what happens behind the scene? Does it does it follow all the typical CFD process? Yes. So what happens is we refer to all these standards in order to calculate the uh, uh, flow performance parameters, as well as the methodology, the simulation flow conditions and pressure tappings, all these things we refer to these standards. And also there are some verification validation guidelines we follow. And then what happens in the CAD cleanup? So it has its own tolerance. It decides, the algorithm decides which gaps to close and which gaps to keep. So it automatically closes these kind of gaps, unwanted gaps, and then it does the mesh generation, very refined mesh. So refinement is also intelligently chosen. So where, near the body, near the moving parts, and wherever there is a geometrical gradient, steps or things, so near the edges of leaders, so further refinement is done. And also in order to capture the boundary layer, there are prism cells continuously created on the surfaces, okay, walls. So on top of this, there is a mesh quality check algorithm which does iteratively improves the mesh until all the mesh quality parameters are satisfied to the up to the designed like defined criteria. Okay. And the solve, we there are some flow conditions. These comes from the ANSI IC guidelines. So what should be the maximum line velocity, max minimum Reynolds number that should be maintained, and pressure tappings. The flow should be, fully developed. So all those things are followed. And there is a turbulence model. Realizable capstone is chosen. Y plus, there is specific thing called Y plus for CFD people, like, so that you need not to worry about. So this algorithm automatically checks whether it follows the required Y plus for this turbulence model, and if not, then it refines and does the necessary corrections. So, and also it's an iterative process, right? So we need to monitor the convergence of the results. So residual convergence, and top of that, the pressure and CV, it should be very flat. Even if you run it further, there should not be any changes in the pressure or CV value. So the solution is converged. So all these things are taken care in the backend. So what happens is you upload a CAD model, and it assigns a dedicated 36 core EC2 Amazon EC2 instance for the simulation. And the simulation hub APIs are called for CAD cleanup, meshing, and solve. And once it is done, then you get the simulation results viewed on the web browser. So you get a CV and CDT. And it is not just for one opening. The same thing happens for all the openings parallelly. So in a conventional method, you are limited by the desktop machine and licenses which is occupied. When you start one simulation, that license is locked, it's occupied. Your other angle of openings go in queue, right? It has to wait for one simulation to complete. Whereas in the cloud, all your opening angles, or that simulation runs parallelly. So at the end of 1 to 2 hours, you get the complete CV curve, not just for one opening, right? So that is the biggest advantage. And all the process happens autonomously. So you get the report at the end of 2 hours. Not just that, let's say you have multiple design options in your mind and you want to quickly run and see and compare the CV curves. Again, same thing happens. There is no limitation on the licenses. It's not occupied. It's distributed kind of, you can each design and each angle of opening of that design gets a dedicated machine, and then it runs independently. So all the simulations, for example, eight openings or 9 openings and 3 designs. All these simulations run parallelly, and then you get to compare the CV curve. That's the so so what it means is it allows multiple teams across different offices of your organization to collaborate. Different teams are working in different lines, like they are working in different valves designs, and they can use the software parallelly because it's on the cloud and simulation. So that's the power of So here is a short comparison between the conventional CFD approach and the simulation of approach. In a conventional approach, you get all the process is manual and it is limited by in-house resources, and the results takes days or weeks. 5 days typically takes 3 to 5 days of time. And then simulation of approach, the process is autonomous and the cloud computing is used, and the results are available in hours. Okay, so yeah, it sounds very fast. It's done, but how about accuracy, right? So this is the validation study I would like to present. So we have conducted multiple validation studies across different valve types and across different sizes of valves. You can see the CV values indicating the valve sizes, flow capacities. So we have tried different tests and the lab test across FCRI and Utah data. So here, what we have observed is all the result shows plus or minus 5% deviation from the uh, lab test data. So let's jump into the details. I picked few tests from this range of tests, validation studies we have conducted. So I'm presenting here. One is DN45 centric butterfly valve. You can see the mapping. It's very matched, closely following the experimental. So that percentage deviation is less than 5. And similarly for DN80 double offset butterfly valve, it's in range of -5 to +5. And this is another double offset butterfly valve, DN200. So again, in the same range. So this is another large size butterfly valve. I told right. So that also we got a one research paper where we are able to match pretty close to the actual values. So both CV and CDT curve we were able to compare with the experimental results. So this was DN 1800. So this paper had that results, and then we were able to compare and match it. So the customer success stories, this includes one real life case study of butterfly valve optimization. So we'll see those. And these are our currently like customers across the globe using Autonomous Valve CFD. To name a few, Bray, Trillium, Redpoint, Delval, um, Cashco, Flowtide. So all of the companies are using Autonomous Valve CFD. So some kind words from Bray, CMO, CTO, and EVP, Brindesh Truva. So yes, so how it helps to reduce the number of expensive physical prototyping and testing required. So this is the case where Bray, what are the challenge? Already they had flow loop test and generic CFD tool and team. But what was happening is each flow loop test used to take for each design, it used to take 3 to 4 months, including the prototype and testing and everything. And that is considerably high. And then the generic CFD tool, the CFD experts were in-house CFD experts were overworked and limited by the number of licenses, and they had a large work backlog of designs in queue. So it takes up to 3 to 5 days to get the complete CV curve for one design, right? Can you imagine that limits the innovation space, like design space, design exploration space, okay? So with the implementation of integration of autonomous valve CFD, then their design engineers started using. It started with 3, and now around 30 users are using across different branches from Houston, Bangalore, and Chennai. So the growth is very good. The usage is also very high. So the number of simulations are crossing 1200, and yeah, even because it's a web app, even during the COVID or remote, period, their design team was working continuously on the design part and in launching a new product. So that helped in a way. So uh, the second case study of the customer service story, I would say, is Delwall. So we have long association with Delwall. So they had started from 3D CAD model and then valve simulations. They started with 300 simulations. Now they are running more simulations and winning big. It is helping them in winning big projects. So uh, I said like there are some real life case studies. So this is what I wanted to show. So they have been, uh, manufacturing large size butterfly valves. So of size 72 inch and 96 inch. Recently they did. It's very large size valves. And then to imagine, you want to test them in a lab facility. First thing is the lab facilities are limited by the capacity to test such high, pipelines, high diameter pipelines, and the flow capacity, pumping power, all those things, right? It's very challenging, very limited, I would say. So we are able to support them, and they have been nicely using the Autonomous Valve CFD application to optimize their design and simulate each and every design. Uh, so with this power of cloud computing, they are doing the design iterations faster, and they ensure each and every design is verified. The flow capacity, whatever they uh, put, is verified and backed up by the data. Okay. So this is one case study where it's a DN 1200 double offset butterfly valve. So they had a design CV target of 1,20,000, and what their baseline design got them was 93. So it was falling short by around 20 to 30%. So what happened was like they, in collaboration with our support team, we quickly uh, did a brainstorming, co-creating kind of session, and then they brought their expertise, and then we analyzed the results along with them, and then we suggested a few things. They confirmed the manufacturability and the structural part of it, and made those changes and to reach the value above the target. So all this happened in a span of 3 hours. So they started with the baseline design, and they came up with the CV value, baseline CV value, and then we collaborated to reach their target CV in due to the cloud platform and things. Yeah. So we can see the power of the cloud computing and autonomous part. So again, some testimonial from GM Engineering. So some large size butterfly valves, and also other type of valves like from Magwin, the plunger valve, 1600 diameter. So they use, and for some organization, we also take consultancy projects. So this was a case of Sierra valves from Egypt. So theirs was axial, or nozzle check valve. So axial flow nozzle check valve. So there we were able to do all the spring related things, and this complete study was done using the support team. So we support both the ways, like you can use the subscription method, and your design team starts using it, and wherever you face some challenge, then our support team jumps in to help you with one specific project or something. Yeah. So this is again Rick Stack, customer testimonial. Again, one more thing. So different it's a strainer valve flow simulation. So some R&D and consulting work at present. So currently we got some success in incipient cavitation, and it is implemented in the app, and liquid recovery factor. So there we are getting some success. So this we are not integrated into the app yet, but we are taking it on a case-to-case basis, consultancy basis. So this is a typical like FL curve for one of the case, like 8-inch double osset butterfly valve. So you can see that. Okay, so with that, we are towards the end of the session. So what's next? You can log into simulationup.com. You can request a demo. You can start your trial subscription, which is 15 days and 20 simulation credits, 20 CFD simulations you can perform. Or you can request a demo and schedule a call with our expert. So we can conduct the detailed demo session for your team, and that way. And also we also conduct validation study. So if you have certain pre tested data, then for that design we can conduct a validation study to gain the confidence and then move on to the next phase. Okay, so one exclusive announcement for webinar registrations, like webinar attendees. So what typically is 15 days trial subscription and 20 simulation credits. So we are giving extended trial for the webinar attendees. So you can reach out to me and mention. You can request a demo on our website. You can schedule a call and mention about the webinar attendance, then we will be able to give a extended trial and submission credits. Yes. So with that, we are towards the end of this session. So we have 10 more minutes we can spend on the Q&As. So you can put your questions on in the chat window. So we'll take those questions. Yeah. Okay. You can use the chat window and okay, so I'll till I get that question. So I'll take some frequently asked questions. Um, so one of the questions we got is like we get regularly is like what about the we already have a team of CFD experts. So what about for them? Is this software only for them for the designers? So I'll let me share some slides. I have separate slide that. So I hope you're able to see my screen. So there is a two different modes. One is the expert mode and the other one is autonomous mode. So in the expert mode, more options, more controls are given to the experts user. Okay, so you have control over mesh refinements, turbulence model, and whatnot. So you can model complex geometries as well using these options. So both autonomous as well as, let's say you have your own SOPs kind of thing, for your team, you follow certain turbulence model and numerical schemes. So that control, we can open that. So you have the expert mode open, then you can control those as well. Yeah. Thank you, Benjamin, for thanks for your appreciation. Okay, glad it was insightful. Yeah. Okay. So any other questions? Okay, I see some. Okay, what about cavitation index? So to be specific, it is about incipient cavitation index. I would like to highlight that. So we do provide incipient cavitation index for the complete opening angle. But for FL, I said we'll take it on case-to-case basis and project related things. Yeah. So yeah, incipient cavitation index is supported right now. Okay. Yes. So do I have some other? Okay, let me share my email. Um, you'll be receiving this recording and of the webinar for your future reference. And you can reach out to me. I have shared my email ID in the chat, praveen@cctech.co.in. So you can reach out to me and yeah. I can help you with any more queries. So, okay, so no other queries. So we can close this session. Thanks. Thanks